Hello, everyone. We have already in part 4 of this course started this parametric classification, and we introduced how to classify between between different attributes based on probability by assuming that they are normally distributed, multivariate normal distributed. Now as a continuation of this part, we talk about another quite simple classification method. Is called logistic classification. So here we study the case where we don't need to compute the mean of the class or the variance or the correlation or covariance matrix. So it is quite simple method. It is almost like the linear classification. However, it is we can call it like smooth classification. What I mean by smooth is that instead of saying that this attribute or this input belongs sharply to class 1 or class 2 in the binary classification, we can say that it belongs to class 1 with that probability and belongs to class 2 with other probability. Of course, we can have a threshold here, like 50%. So if the probability of being in class 1, for example, is more than 0.5, then we take this to class 1, and if it is in class 2 with less than, or if it is with the probability of being in class 1 less than 0.5, then we take it to the class 2, because in the two classes case, we will have like the total probability equal to 1. So the probability of being in class 1 plus probability of being in class 2 will be 1. What is the benefit of that? Actually, we have several benefits, as we will see them. So it is easier to compute. And another nice property here, that for some classes, especially that when you compute or you want to predict the class of a new input for a new attribute, then if you get, for example, 0.9, the probability of being in class 1 is 0.9 or 0.95, then you can have like more trust in this classification. If it is, for example, 0.55 or 0.52, then it can be in class 1 or in class 2. So in this case, it could be the reason that of this deviation due to some noise or some biased data. So it gives for the like wider vision of the interpretation about the classification of data. Okay, now let us talk a little bit about this classification. If I just change to the pointer, yeah. So this is what we know previously from part 4, that the probability of being in class C1 based on this data input of data attribute X, this could be handled by Bayesian theorem, as we know. And when we assume that the data of or the distribution of attributes based on each class is multinormal or multinomial distribution, normal distribution, this could be done in this way. And since we have only two classes, then the probability of being in class 1 based on X is equal to 1 minus the probability of being class 2 condition on the input X. Okay. If we divide probability of being class 1 but by the probability of being class 2, this could be solved in this way. So it is probability of being class 1 divided by 1 minus probability of being in class 1, because we have only two classes and the summation of probability is equal to 1. And if you divide these equations, of course, you can see that the evidence of the distribution of the data will cancel each other, and then we will have this form. And by substituting this, we will get the general form of this division. Now we can, by taking the logarithm, we will have just this equation, which is actually like quadratic equation, as you can see it here. But in case that the covariance matrix of both classes are quite close to each other, then the equation will be linear in this case. And then in this case, we can assume it in this way. So logarithm of probability of class 1 conditioned on the input x, 1 minus probability of class 1 conditioned on x equal to the linear equation, as you can see it here. So it will be this weighting vector wt transpose times x plus w0. Now we can take exponent of both sides and we solve for the probability of being in class 1. And by solving this, we got this equation. So the probability of being in class 1 given or conditioned on x should be 1 divided by 1 plus e of the power minus w transpose is the weight transpose times x plus w0. W0 is the drift of this linear equation. So actually, this is the probability of being in each class. So, and this could be done in this way. So we put here estimation that b hat as the estimation of the probability. It will be given in this way. So now we might have any probability from 0 to 1. So not to saying that for sure that we are in class 1 or in class 2. So now we have probability of being in class 1 and then the probability of B in class 2. So if the probability for the input data xi to be in class 1 is equal to yi, as it is given here, so the probability of the same input to be in class 2 is 1 minus yi. Okay, now actually we can apply this over a simple case or simple example to see how to solve it. So now we have inputs like x1 and x2, and for every attributes input we have the classes. This is in class 1 and class 2, class 2, class 1 and class 1. This is data that we have like before. So it means that if we assume that the probability of class 1 given the condition of the data, class 1 is equal to 1, and this is a class 2, which means that the probability of being in class 1 is equal to 0. This is in the training or the training data. Okay. Now, what is our aim? Our aim is to find the optimum W, weight vector W, and also the drift W0, in order that we got the best fitting of this of the data that you have. Okay, and why it is called logistic classification, because this equation is called that logistic equation. This equation, so model function or logistic equation, because we take the log for that function. Now, if we build the likelihood of the data that we have seen this in part 3. So the likelihood will be the multiplication. This is yi. Remember that yi here is the probability of being in the class 1. Okay, conditioned on the x. Okay, so now if we define ri equal to 1 if this x belongs to class 1, and equal to 0 if x belongs to class 2. Okay, now if assume that we have n data sets in the in our problem. Here we have 1, 2, 3, 4, 5. Here we have 5 data sets. So it means that n equal to 5. Okay, so we start. What is the probability, the binomial distribution of being with certain case? So the first input here, it is in class 1, which means that will be y1 in this case. y1 of the power of 1, so it is y1. But 1 minus y1 here will be power of 1 minus 1 is equal to 0. So this will be 1. This will be 1. So it will be y1 times what? Times for the second element, it is in class 2. So for the second input, this will be times 1 minus y2, because in this case now we have the second element belongs to class 2. So for every class 1 we multiply with y, and for every class 2 we multiply by 1 minus y. This is the reason that we have this multiplication. And actually, this was discussed in part 3. Okay, now we want to build the, what we want to find. We find, remember, that we want to compute the optimum weight vector W and the drift W0, okay, which maximize this function, maximize the likelihood. Then we have the maximum likelihood estimation as we explained in part 3. And maximizing the likelihood is the same as minimizing the cost function. And the cost function, it will be, as we know that a maximizing function, if you take the negative of this function, it will be like minimizing the negative of this function will be like maximization. So it is the same here. We take negative sign, but we take log, and we explained why we take the logarithm in part 3. We explained it in details there. So we take log for this multiplication, converting from multiplication to summation. It becomes much easier to solve. And then we have this minus sign. So now we want to find W and W0, which minimize this cost function, okay, to minimize this cost function. So it is quite straightforward now to solve. And before that, we want to remember a few math tips here, that if you have this yi function in W and you want to differentiate it with respect to W, so the differentiation for the log of yi is equal to 1 divided by yi times the differentiation of yi with respect to W. And we have, this is yi that we have, and then the differentiation of yi with respect to W, we can simplify it with a chain rule, and then it gives us yi times 1 minus yi times xi. Xi is the input, and then dyi with dw0, the drift, will be yi times 1 minus yi. So now what we need to do, this equation, actually this like cost function is nonlinear. And since it is nonlinear, so in order to find the weight vector, we need to use the steepest descent algorithm. The steepest descent algorithm was explained in detail in part 2 of this course. So you can go back to part 2 to see how it works. But the idea here that the steepest descent, that we can adapt the weight in this way. So the weight at time k plus 1 equal to the previous weight at time k minus the adaptation rate mu times the differentiation, the partial derivative of the cost function with respect to the weight. And of course, we need to do it with the weight vector and also with the weighted direct. So this is what we are showing here. And then we make this derivation. So this derivative. So we take the derivative with this function with respect to W. So we show it here in details how to do it. So you take the differentiation inside. So this will be Ri divided by yi times the derivative of yi with respect to the weight vector W minus, because when we take the derivative, this will be minus. So it will be minus 1 minus Ri divided by 1 minus yi times the derivative of this function, and derivative of 1 is 0, minus, it becomes outside here with Wi with respect to the partial derivative of yi with respect to the weight vector W. And we know that the derivative of yi with respect with the derivative is W with the weight vector as we showed here. So this derivative gives us yi times 1 minus yi times xi. So this is what we can substitute them here. And when you substitute it here, yi cancel yi, and here 1 minus yi cancel 1 minus yi, and we have xi as a common vector outside. And just make this expand this equation. Finally, we will get this the final equation that the adaptation factor will be the summation of yi is the probability, or the estimated probability of each input minus Ri. This is the hard probability. It can be 1 or 0, okay, times xi times the input. This will be the optimum adaptation like factor here in this equation. And the same we can do it for W0 for the drift, and this gives us this equation. And now we have finally, this is the adaptation weights for the logistic algorithm. This will be the adaptation weight that it can be easily implemented by using any programming code. And actually, I did it for Octave or MATLAB, and we have this is the whole code to compute it. So the code will be available in Model if you want to try it, but also you can use ready functions for logistic optimization. And this logistic optimization, actually, it can be extended easily to be multiple classes, more than 2 classes. But the idea here is to show the concept of using it. Also, I will record one short video how to use this function and how to use it for logistic classification of 2 classes and also for multiple classes. Thank you very much.